Hi, this is Alex Zaitz of Audio Zenith, company that modifies Oppo PM1 and PM2 headphones. Um, and this recording is being done in a slightly acoustically treated room, and I wanted to demonstrate to you the effects of the room itself that makes uh, my sound my voice to sound way more natural, way more realistic, with nothing added. Not much added to it. I hope you can clearly hear all that, and I will pan my camera around so you can see that the room has about the same size, not much of a furniture, with the exception of a couple of chairs and a few loudspeakers. And that acoustical treatment is very, very light. You will see, there is some panels with foam inside, but they are very thin. Nothing major, nothing special, nothing expensive. Anyone can do that at home. So take a look. As you can see, room makes a huge difference to sound uh, of a recorded voice or instrument. And how is it related to headphone reproduction? Well, the headphone enclosure and the ear pad and the system that the whole coupler makes a huge difference to sound of that particular transducer. It's the same exact system, same triangle. Our ear is in one corner of that triangle. Our transducer headphone driver is in the other corner, and the third corner is the ear pad and the coupler itself. Same as with the listening room, where you have a listener sitting in his listening chair. You have loudspeakers and placed in the room properly, hopefully, and the room itself. So, from this point, I wanted to take another example. Two headphones. One would be original Oppo PM1 and PM2 that I feel sounds polar opposite to something like Sennheiser HD800 in terms of imaging and sound staging. Many people complain about original Oppo headsets that they sound a bit enclosed. The imaging is not wide, and sound stage is not big. Imaging is not precise or overly, actually not precise, but like kind of smaller, more dense, versus its polar opposite, which is HD800, where many people complain that it sounds the sound stage is exaggerated, artificially exaggerated, artificially enlarged, and imaging is diffused. And the reason to this phenomena is the coupler of original Oppo PM1 and PM2 is quite small. As I said in the first video, and everybody knows that average size ear barely fits within the ear pad, and there isn't much space within the ear pad and between the driver opening and the ear, and the ear pad itself is quite has a quite thick layer of foam, so it almost sounds like it's overdamped, and that's what people complain about. And it reminds me a bit of listening to a loudspeaker in an acoustic chamber. And Sennheiser HD800 is a polar opposite. I have it here so you can take a look. You can see that the coupler consists of a driver, which takes approximately, I would say, about 50, anywhere from 40 to 50% of the inner volume of the enclosure, and the rest is a steel mesh. Okay, and when this material takes that much space within the enclosure, you have a lot of reflections. Some of those reflections are good, and they increase the image and they make it sound a little bit more natural, but some of it is not good. It's like listening to a set of loudspeakers in an empty room, untreated room. And that's where some modifications are going. You can see people inserting damping to cover some areas inside, and people insert some foam to cover the mesh, and so on, in order to mitigate this problem with diffuse imaging and artificially enlarged soundstage. So the point is, the coupler has to be properly designed. All this, it cannot be it cannot have too many reflections, and it cannot be overdamped. So that concludes my first part of it's like an add-on to a first part of a video where you can see what effect the enclosure or a room makes to a sound of a loudspeaker. And then I have the PM1 or PM2 driver here, and I will start explaining what modifications it undergoes before it becomes Audio Zenith PM2. The first thing that we do to a driver, we thermally treat it. It goes, it's not exactly an oven, but almost, something like it. It goes into an oven for 48 hours. We started doing it a while back, and we did several pairs, and we stopped. Why did we stop? Because it was too complicated. We thought it was too complicated, and the gain was not worth it, even though we saw that we were getting frequency response extended a little further, both in the high frequency department and in the low frequency department. But we could have achieved, we knew that we could achieve similar gains with simpler modifications. And on top of that, we try to do to speed up the process and increase the temperature within that oven and fried a couple of drivers. So that kind of stopped the whole thing for us, and we forgot about it for a few months. Up until we got one of the drivers, one of the headsets that we made using thermal treatment. We got one of those sets back and we measured it, remeasured it. And we were surprised by the low frequency and the high frequency extension that we couldn't match with the current production units. So we said to ourselves that if we can have these gains, we better do it. So we continued doing the thermal treatment, even though it is quite dangerous. It is very complicated and it takes a lot of time. We still want to do it because we like the low frequency extension very much. As well as high frequency, it's not that big of a gain in the high frequency, but there is still a gain. So that's the first thing that we do to a driver. Second thing, once we take it out of that oven, we retension the diaphragm. As you all know, the tensioning of a diaphragm in planar magnetic drivers is the absolutely crucial part of of the driver's performance, and as an end result, the frequency response. But unfortunately, it's very difficult to make consistent tensioning. So when you take two drivers from the same set, they're not gonna have the same tensioning, and that's our second step. That's what we do. We modify the tensioning of a diaphragm so that it matches for both drivers in a pair. Even though we do that, we spend time and effort on tensioning, it still doesn't come out exactly the same for both drivers, but it just gets closer. It narrows the gap. The third thing that we do, when you have a driver, and by that point drivers are assembled, most modifications are in place, and it undergoes first measurement. So we measure two drivers that are going to become a pair, and we see differences in the frequency response. To mitigate those differences, we have to realign the magnets within the driver. So we have to realign both front and back magnets. And not only that, we could make a distance. We varied a distance between the front portion or front side of a diaphragm and a front magnet, as well as we vary a distance between the back side magnet and the back side of a diaphragm. So distance between the diaphragm and the front magnet could be one, and the distance between the back side magnet and the back side of a diaphragm could be the other, or they could be the same. It depends on the tensioning and the measurements. So we can, And we cannot calculate it, unfortunately. We measure it and we see what needs to be done approximately. Then we make those changes, either increase or decrease the distance between the driver and the magnet, front and back. Remeasure again, see if we got where we want it to be. If not, we redo it. Again, either decrease or increase. Very, very, very difficult process, very time consuming, takes quite a few measurements and quite a few ways of realigning the magnets within the structure. Then what we do is we add our own magnetic structure on top of the original in order to amplify some portions of a frequency response where we need where we feel it's needed. So we add our own magnetic structure to the back side of a driver in order to reshape the frequency response and make it more make it quicker, the diaphragm itself, by increasing the flux density of a magnetic field. I hope many people understood what I just said. But yeah, I'm trying to use as simple of terms as I can come up with. So we add on our magnetic structure. It improves frequency response, as well as it makes driver faster, makes the diaphragm move faster, and decreases the distortion. Then what we do is we start working on the front and back wave and the motion of a diaphragm itself. Any driver should have, ideally, should have pistonic motion. It should move like this. When it starts moving like this, it's no good. Distortions, bad frequency response, and all kinds of problems you can think of. So pistonic motion is what's needed. Now, when you look at this driver, this is the front of it, okay? It has just this opening. And you look at the back of a driver, and it has the same exact opening here in the center. And in addition to it, you have a whole bunch of holes surrounding that original opening. So front side and the back side of a driver are very different. What does it do? It makes diaphragm move like this instead of like this. It goes like this because sound pressure in the front of a diaphragm is different from the sound pressure and distributed differently. That's the word. From the sound pressure and sound waves that are generated, that are playing in the back of the driver. To mitigate that, the simple way would be to damp it with two different materials, right? So you would do, or just block the all these holes, right? so that front wave will equal the back wave. Doesn't work like that. It has to be damped a certain way for diaphragm to become more pistonic, for diaphragm's motion to become more pistonic. So you, for example, you take two different materials with different acoustical properties, with different damping factors. You apply them to the back of a driver, you put them between the back of a driver and the enclosure itself, and you can stabilize the membrane, its motion. But because it's gonna be two different materials, those materials will have different properties, and reflection of a back wave from those different materials is gonna affect different areas of the diaphragm differently. Okay, it's like here, for example, softer with more absorption, here stiffer with less absorption, more reflection. That will introduce some different problems and issues. So the diaphragm, instead of going like so or like so, will be something like this. Okay, so back wave is gonna difference in the back wave throughout the surface of a driver of the diaphragm is gonna affect what will come out with the front wave. It's gonna affect the diaphragm and in the end the frequency response. So how do you do this? It appears like, it appears to be impossible to combine these two things. Make diaphragm more pistonic and get rid of the differences in back wave affecting the diaphragm itself. And we were able to find a certain material that was originally developed for NASA to be used in their space projects, which has incredible acoustical properties. And as far as I know, no one else uses anything like it. It's a great material, and it did help us in mitigating those issues in the back of a diaphragm. It is so unique that it's not even being produced all the time, so you can't, like right now, I can't even buy it myself. I will probably have to wait for several years for it to be manufactured again. So it's being manufactured in the very small quantities, and I was able to get as much as I could, and now I'll have to wait. Hopefully there won't be much of a demand for audio Zenith PMx2, so that I'll have enough for a few years of the stock of that material that I got. But even though it's so unique and hard to find, it made our life much easier because it increased consistency of our backside damping, and consistency of our drivers made our lives easier, and now it has a lot less distortion to 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 a frequency response. That was another part that we do to an actual driver. And now enclosure itself. Original enclosure has some ridges, something similar to what I was talking about in the first video. So some ridges as well as some rips that we think could be the cause of some of the reflected wave going back to a membrane, affecting frequency response. So we had to modify the enclosure itself, the back portion of it, back side of it, to get rid of some of those rips and improve that side of a driver. On top of all of that, once everything is done, each driver went through some measurements, preliminary measurements, alignments, retentioning, some more alignments, magnet alignments, and so on and so forth. Then we measure it again, and we take those two drivers and we try to bring them closer in frequency response to make it the real pair within our standards. And our standards are very, very, very high. The frequency response throughout the entire range, well, almost entire range of this driver lays within plus minus 1.5 dB, anywhere from approximately 42 Hertz all the way to 14.5 kilohertz, plus minus 1.5 dB. Loudspeaker manufacturers strive to get close to plus minus 3 dB with loudspeakers. And loudspeaker doesn't make the whole sound in the room. You have room added, and then frequency response you see becomes anywhere from plus minus 5 dB all the way to plus minus 20 dB. And when we talk about headphones, measured frequency response is the actual frequency response within the coupler. It's like measuring loudspeaker in the listening room, in the actual listening room where you will be listening to that loudspeaker. So, and yet our standard is plus minus 1.5 dB within the coupler itself. The end result. To get to that, not only we have it plus minus 1.5, we try to match both drivers as close as possible to each other. And that takes some extra work done to both back damping and the front damping. So some extra things are added, and you can see, you can actually take two drivers left and right of one finished set, and both front and back damping will be slightly different. Slightly different materials are going to be used in both, and quantities of those materials could be different, all in order to bring frequency response of those two drivers closer together. And sometimes, believe it or not, but sometimes it takes 50-60 measurements of both drivers before we come to an end before we have a complete set. And of course, it takes a long time. It takes a really long time to do each set of Audio Zenith PM2 headphones. And I understand that, and you should understand this too. Some of it comes from planar magnetic drivers themselves being very inconsistent, and every planar magnetic driver manufacturer experiences this. But the question is, can anybody do this in a large scale? Does it make any sense to be done on the factories? I honestly don't think so. I honestly think that no one's gonna do 50-60 measurements of drivers, trying to match them closer together, trying to bring the response of a driver closer to plus minus 1.5 dB. It makes no sense financially. It just makes no sense at all. So therefore, I don't think we will ever see, unless somehow technology progresses so much, so that we will see more consistency in the planar magnetic drivers. But I seriously doubt that. I seriously doubt that that it's going to happen anytime soon. But we have what we have, and I'm not complaining. I'm just trying to explain what's going on, why it takes so much time, why, and time is money. You cannot go away from that. It's pretty much non-profitable. But I want the people to be able to hear neutrality. So that's the thing. That's my thing, and hopefully it will be appreciated. Maybe later. But that's what it is, and I will be talking more about neutrality in a sound reproduction, its importance. I will be talking more about the human hearing system, its physics, what's going on in the nature, and why it is important for us to not go away from it, to be able to hear recordings the way they were meant to be heard by artists, composers, recording engineers, producers. So look forward for the additional videos, and I thank you so much for your time, and hope to see you soon.